Welcome to Sigma Solver guys. Before I start the video, I want you guys to smash the like button. This helps the YouTube algorithm and keeps me motivated. And if you are new here, then subscribe to my channel and press the bell icon so that you never miss an update. So without any further ado, let's get started. So today we are going to discuss chromatic polynomials, which is an important topic in graph theory among many others which you will discover. And let's find out what the question is trying to say. So the first thing is find the chromatic polynomials of each of the 6 connected simple graphs on 4 vertices and verify that each of the polynomial has the form lambda power 4 minus e lambda cube plus a lambda square minus b lambda, where e is the number of edges and a and b are positive constants. So the question is simple. And we are given 2 important terms. One is chromatic polynomial, which we'll come across soon and see what it is all about. And another one is connected simple graphs. So a connected simple graph is like any other graph with nodes and edges, such that there is no self loop and there is no parallel edges. So a graph, let's say having 4 vertices and having this particular edge as well. So this is a not simple connected graph. Or if suppose 2 particular vertices have 2 edges between them, like 2 parallel edges, then again it will be a not simple connected graph. So that is what simple connected graph means, and we have to find 6 of these, right, with 4 vertices. So the number of vertices is fixed and we have to calculate 6 such graphs which are simply connected and find the chromatic polynomials for each of them. So before we move ahead, I will discuss what is chromatic polynomial first. So chromatic polynomial for a given graph G is a function that counts the number of ways to color the vertices of G using k colors, mind it, such that there are no 2 adjacent vertices having the same color. The second part of the definition also denotes what is called proper coloring, right? So coloring a graph in such a manner that no 2 adjacent vertices are of the same color is also called proper coloring. So that is what we are trying to achieve, and we are given a particular set of or a particular number of colors. We need to find out what are the number of possible ways that we can get the graph properly colored. So let's move ahead with this. So this means, as I have tried to make it in simple words, the value of the polynomial at k gives the number of valid k colorings of the graph. So the polynomial is obviously a function and it will take k as input, and the result that it will show is basically the number of valid colorings where no 2 adjacent vertices are of the same color, and return it to the output screen. So that is the brief introduction to chromatic polynomial. Now we come to properties of chromatic polynomial. So the first property is the polynomial nature. The chromatic polynomial is indeed a polynomial in k, right? So a polynomial in k simply means like it will be the same exact form, a raised to power n k, a raised to power n minus 1 k minus 1. So that is how like it will go, and we will see that in a while. For a graph G with n vertices, so the chromatic polynomial is a polynomial of degree n. Okay, and this is how we are going to define it. Next is coefficients and terms. So in that we see the actual polynomial figure or the form in which we are going to consider the chromatic polynomial. So in this, an is basically the coefficient of the maximum power variable, that is k raised to power n, and that reflects the fact that the highest degree term represents the dominant behavior of the polynomial for a large k. So as it is quite obvious that if an had not been 1, then its value would drastically change the number of chromatic polynomial. So we need to make it 1 so that the value of k raised to power n has its dominant nature in the polynomial's value, as well as we don't overpower it. Then we come to some basic points in regarding to chromatic polynomials. So first of all is PG0. This means that a graph in which we are given 0 colors to choose from. So in that case there are basically 0 possible ways to color the graph. Similarly, if we are given only one color, right, and we are given the entire graph, we cannot color the graph only, because if it is a simple connected graph, then each vertex would have been connected to other vertices and there would have been edges. And if that is the case, then if we take this as the first vertex and color it with say color 1, then we cannot color the other 2 that are joined to it. So then we can say that this is also not possible and not valid. Hence the number of ways in which we can color the graph is 0. Similarly, if we take, let's say, PG2, this means that in the graph we are only given 2 colors and we need to color it, and suppose it comes out to be 2, let's say it comes out to be 2, and then we can basically use it to check if the graph is bipartite or not. So like we have K33, so that is also 2 colorable graph, and there are 2 ways if we are having 2 colors to color the graph. So in that way we can check if a graph is bipartite or not. Okay, now we come to the actual calculation part. So in the calculation part, what we were given is basically find the 6 different types of graphs and make the chromatic polynomial out of them. So let's see the first one. So this is basically the first graph. You can see this is a simple graph, and in this we have this PGK. If we try to find out what would be the actual number of ways, so let's say I take this as 1. So I have lambda colors to choose from here, right? Similarly, the adjacent color will have lambda minus 1 ways to color. Similarly, this one will have lambda minus 1, because only the lambdath or any other ith color is missing since it is joined here, and here also it will be lambda minus 1. So you saw that we are only taking lambda minus 1 ways to color each graph except the first one. So that is how we can calculate it, by simply multiplying it, and then we get, when we expand the expression, we get this particular expression. Okay, now we move on to the next graph. So this is also another form that can be generated as a simple connected graph. So this is K13, right, and you see that only one vertex is there who is actually connected to all the other 3. So we can bring these 3 into a set and this one into another set, right? So that is why it is K13. So we can bring the number of vertices into 2 sets and color them accordingly. So the first one can be colored, like suppose this one can be colored in lambda ways, and the other 3 can be colored in lambda minus 1, so its power is 3. So thereafter similarly we can expand it. Next we come to the actual cyclic graph, which is a bit more detailed. We have to take the first color, and let's say I painted this. Then we can either go to this particular vertex or this particular vertex. We can either choose this particular vertex to start from. Similarly, like all the ways needs to be considered before we actually jump into the answer. So we'll look into it, basically how we can find it, but for now let's assume that this is the actual representation of the value right now. So it will make more sense when I discuss it further. Let's come to this graph. So let's take this one as the first vertex, so it will have lambda ways. Let's take this one as the second vertex, so it will have lambda minus 1 ways. Again this one, if we take, it will also have lambda minus 1 ways, right, because they are in line and it will have that. But if we see this particular vertex, it is connected to both this vertex and this vertex. So let's suppose I used red here and I used blue here, then I cannot use either red or blue, so my color will be different, let's say green, right? So you saw that we are actually subtracting 2 colors from the set, so therefore this will be lambda minus 2 ways. So similarly we can have this particular equation there, and when we expand it we get this. Then we have this particular graph in which again let's say I take this one as the first one, this one will be lambda minus 1, and consequently we can see that this one will be lambda minus 2 and this one also will be lambda minus 2 because they are connected in two ways. Like here also it was connected in two ways and the other one is also connected in two ways. So we can see that they both will be colored in lambda minus 2 ways, and here is the expression for that. So then we come to the last part, which is the complete graph of 4 vertices. So it's quite easy to tell what is the chromatic polynomial in that case, which is sort of factorial kind of, like lambda into lambda minus 1 up lambda minus n, that is the number of vertices. So if we expand it, we get this, only because we have this one as first, so lambda, then we have lambda minus 1. You see that we are connected in two ways, so we have to give it lambda minus 2. Now you see we are connected in three ways, right? So it will be lambda minus 3. So that's how we come to this point. Okay, now we are going to talk about the cyclic thing that we missed out previously. So in that case, what we are going to do in that cyclic scenario is basically we are going to calculate the entire number of ways by adding the number of ways in which C4 has a pair of non-adjacent vertices that are colored the same, a way in which these two will be the same colored. So then what is the number of ways in which we can color the other two, and that's what we are going to discuss. So in that case, we get it lambda into lambda minus 1 square. Why? Because we have only one vertex to choose from at the first time, and then both the other twos are getting lambda minus 1, and similarly the other one will be again lambda minus 1 only, because they are both colored the same, so it will be lambda minus 1. The second part is the number of ways in which that pair can be colored differently. Two vertices that are opposite to each other needs to be colored differently, so they will be having the two vertices that remain will be having lambda minus 2 ways to color it, and the first one that we will choose is obviously lambda ways. The adjacent to it will have lambda minus 1 ways, but the other two will be having lambda minus 2 ways respectively. So, and the last part of the question says verification. So let's take any of the examples. So what the question was, it says that verify that the polynomial has this particular form. So if we consider the first one, you can choose it with any other form. The first one is obviously always 1, the next one is E, the next one is A, and the last one is B. So here it will be A and the B part will be here. So that's how we verify it with all of the forms, right? So that's it. If you still have any doubts in this question or in this topic, then feel free to reach out in the comment section below. If you liked this video, then give it a thumbs up and subscribe to my channel for the upcoming videos. Till then, happy solving.
Hey there, before you go, I've got some fantastic content lined up for you. Over here, we've got some videos and playlists you might enjoy. But first, if you haven't already, make sure to hit that subscribe button and ring the notification bell so that you never miss out on any of our future uploads. Thanks for watching, and I'll catch you in the next video.